Let us continue our discussion of the continuity equation by looking at example 1. A feed water heater is operating at steady state. The feed water heater has two inlets and one exit. At inlet 1, water enters with a pressure of 700 kPa and a temperature of 200 degrees centigrade with a mass flow rate of 50 kilograms per second. At inlet 2, liquid water enters with a pressure of 700 kPa and a temperature of 40 degrees centigrade through a 30 centimeter squared pipe. At state 3, saturated liquid water exits with a volumetric flow rate of 0.07 cubic meters per second. We want to determine the mass flow rates at inlet 2 and exit 3, as well as the velocity at inlet 2. To begin, we will write down all our pertinent state variables. At state 1, we have water entering at a pressure of 700 kPa and a temperature of 200 degrees centigrade with a mass flow rate of 50 kilograms per second. At state 2, we have water entering at 700 kPa, a temperature of 40 degrees centigrade through a cross-sectional flow area of 30 centimeters squared. At state 3, we have a pressure of 700 kPa, a quality of 0, and a volumetric flow rate of 0.07 cubic meters per second. Now if we draw our system schematically, we'd have the following. We have a tank with two inlets designated by 1 and 2, where we have m.1 and m.2 entering respectively. At exit 3, we have m.3 exiting our system. Now if we express our continuity equation for an open system that's operating under steady state, we see that our time rate of change of mass, dm dt, is equal to 0, and we are going to sum our mass flows into our system from I is equal to 1 to 2 of m dot I, less our mass flows out of our system from j is equal to 1 of m dot j. Thus, we can re-express our continuity equation as 0 is equal to m dot 1 plus m dot 2, which represents our mass flow rates into our system, less m dot 3, our mass flow rate out of our system. We already know our mass flow into our system, m dot 1, and we have two unknowns. Let us first start with our mass flow rate at state 3. Recalling our expression for mass flow rate, m dot is equal to rho AV, we can re-express this in terms of our specific volume, such that m dot 3 is equal to our cross-sectional flow area times our velocity per our specific volume. Our cross-sectional flow area times velocity is identically equal to our volumetric flow rate, and this is per our specific volume at state 3. Thus, at state 3, we know our specific volume is equal to that of our saturated liquid specific volume taken at 700 kPa, which is 0.001108 cubic meters per kilogram, and we're given a volumetric flow rate of 0.07 meters cubed per second. If we evaluate this expression, our mass flow rate at state 3 is found to be 63.177 kilograms per second. Now that we have m.3 solved for, we can go to our continuity equation and solve for our mass flow rate at state 2. m.2 is simply equal to m.3 less m.1, or 63.177 minus 50 kilograms per second, which gives us a mass flow rate at state 2 of 13.177 kilograms per second. Last but not least, we have to determine our velocity for our water entering at inlet 2. If we recall our schematic for a cross-sectional flow area, if we have mass entering our system with a velocity through a cross-sectional flow area, we can express our mass flow rate, m dot is rho AV, or solving for a velocity at state 2, this is equal to our mass flow rate at state 2 per our density times area evaluated at state 2. Now if we re-express our density in terms of our specific volume, our velocity at state 2 is equal to m dot 2 nu 2 per a2. Our specific volume at state 2 is going to be equal to that of our saturated liquid specific volume evaluated at 40 degrees centigrade, for this is a compressed subcooled liquid. Thus, our velocity at state 2 would be equal to our mass flow rate, 13.177 kilograms per second, times our saturated liquid specific volume, 0.001008 meters cubed per kg, per our cross-sectional flow area, 0.003 meters squared. Thus, evaluating this expression, our velocity at state 2 is 4.427 meters per second.